Topic 4 is titled Rational Functions. In Lesson 4.1, we will look at inverse variation and the reciprocal function. For inverse variation, you'll have one variable increasing while the other decreases. There are two ways to write out that formula. Take the product of two variables, x times y, and that will always equal a constant, or you can get y by itself and have y equals a constant divided by x. The constant of variation k is simply a number that relates those two variables. In the tables at the right, do they represent inverse variation? If so, write the equation. What we'll do then to test that is we'll multiply x times y. In each column, we'll see if the product is the same or if it's different. In that first column, 1 times 12 is 12. 2 times 6 is also 12. 3 times 4. We're getting a consistent output here for their product. Since the product is the same, we would say yes, it represents inverse variation. And the constant that relates the two variables, k, is 12. For your equation then, we could write it one of two ways. Either x times y equals 12, or to get y by itself, we can write it as 12 over x. In that second group, if we take a look at the product of x times y once again, I notice in the first column 1 times 20 is 20, but then in that second column 2 times 17 is 34. Since they're not a match, they're instantly not an example of inverse variation. And if it doesn't represent inverse variation, we're not going to write an inverse variation equation that models it. Using a different scenario, we have some steps to follow to help write equations using inverse variation. When you know you have inverse variation, we're going to start with the template. And you can start with either template. I like starting with x times y equals k. That way you're not dealing with a fraction. You'll always have information in the word problem, so we'll use information to solve for k. The constant will be this value that doesn't change throughout the word problem. And then we'll rewrite the template. And then if there's anything additional they want you to solve, we'll just find our additional solution. This is a really easy set of steps to walk through. In example 2, it says, in an inverse variation, x equals 10 when y is 3. Write an equation to represent the inverse variation. Then find the value of y when x is 6. Negative 6. So we're actually asked to do two things here. The first thing we'll do is we'll write our equation. In the very first sentence, it says inverse variation. That will always help us start off with our template, x times y equals k. It then says x is 10 when y is 3. That second set of information is useful for step 2 to help us determine what k equals. If x is 10 when y is 3, what will our constant equal? Our constant should just be their product, which is 30. Now that's not the equation, that's just the constant. So asked to rewrite the equation or write the equation, we would go back to our template, x times y equals 30. That's the equation that represents the inverse variation. It says then find the value of y when x is 6. So when x equals, or I keep saying 6, negative 6. When x equals negative 6, we're literally just substituted in. That's why these are so easy to work with. To get y by itself, divide both sides by negative 6, and y would equal negative 5. When you see problems like that, this is the process to follow. When working with inverse variation in application problems, they may write the wording differently than inverse variation. For example, they may say that something varies inversely as something else. And that wording is going to be significant when you have the phrase varies inversely. Whatever variable comes prior to that is going to be the y value or the output, and whatever variable is written after that phrase is going to represent x or your input. Let's see how that plays out with this guitar over on the right. It says on a guitar, the string length S varies inversely with the frequency f of its vibrations. The frequency of a 26-inch E string is 329.63 cycles per second. What is the frequency when the string length is 13 inches? So changing the length of the string will change the frequency of the vibrations on the guitar. To come up with our answer to the second question, we must first generate our model using our set of steps up above. The first thing you want to do is apply the appropriate template. X times y equals k. So now we need to think about, well, what does x represent and what does y represent? Looking at the wording, it says S varies inversely with frequency. And if we follow kind of the model on the left, whatever's written before the varies inversely is like the y value or the output. Whatever is written after the word inversely is going to be your input or your x kind of focus on your, or in your equation. So if we substitute those values in, we actually would end up with F times S equals K. The frequency the frequency times the string length for each guitar, or for the guitar. So using that information, it says a 29-inch E string has 329.63 cycles per minute. So that would be the frequency of the vibrations. That means in step 2, the frequency is 329.63 times a string length of 26. And that will be our constant. If you multiply those two numbers together, we get a much bigger number, 8,570.38. That would be the constant. And again, we want to use that number to generate a formula. This isn't our formula. That means if we go back to our template, F times S is always going to have the constant of 8570.38. That model will help us in our final step. If we change the length of the string, what should happen to the frequency of the vibrations? It should go up because this is inverse variation. Let's see how that's going to work out. If the string length changes to 13 inches, that's going to be our S variable. And when we plug that in, we would have F times 13 equals 8570.38. Divide both sides by 13 to isolate the frequency. Plug that into your calculator, and you're going to get approximately 659.26. And the label, let's go back up to the top. The label is cycles per second. So I'm just going to write CPS for cycles per second. So as one variable increases, the other decreases. The last thing I want to cover in the video lesson is a brief review of domain and range. Remember, domain represents all your possible inputs. Range represents all your possible outputs. And you can write them in both set notation and in interval notation. So let's take a look at the examples on the right. Notice for the first example, it says determine the domain and range for each function. In example A, f of x equals 2x plus 1. This is an example of a linear function. And when we think of lines, lines go to the left and right forever and ever. That means in your domain, x can equal all real numbers. It can be anything it wants. And back in topic 1, so this is a while ago, we used that unique R symbol to represent all real numbers. Using interval notation, though, we said that x could go from negative infinity on the left to positive infinity on the right. And the nice thing about linear functions is both the domain and range have the same set of values. We only need to remember that the range isn't x, it's going to be the output, which in this case is f of x. but it has the same output options. It can be anything it wants. It would also be then from negative infinity to infinity. But rational functions aren't linear. So as we think about how domain and range tie into this topic, notice examples B and C are similar to one of the template options for inverse variation. Now we've got x in the denominator, and that's going to have a significant impact on what we can plug in for domain and what kind of values we can get for our range. When we have a fraction, the rule for fractions is the denominator can't equal 0. So as we think about domain and what possible x values would work, well, x could be 1, it could be 7, it could be 2/3, it could be negative 19. In this fraction, it just can't equal 0. And that's how we would define the domain. X can't equal 0 because 1 divided by 0 doesn't exist. Now in interval notation, it's a little trickier. On the left side, it can go to negative infinity and get infinitely close to 0, so I'll use a parenthesis, but then from 0, it can continue on all the way to positive infinity. Within that fraction, if the domain has x not equaling 0, for the range, if we have 1 on top, we would never have 0 as an output because you can't divide 1 by a number and get 0 as the answer to your fraction. Therefore, for g of x, that's our output, it also can't equal 0, which is pretty unique because then our interval notation does the same as it did up above. Here's the situation though. Anytime you change both the numerator and denominator, now all of a sudden our domain and our range will not be matching. Look at h of x. Now we have 2x plus 6 on top and 3x minus 4 on the bottom. To start with domain, recognize that the denominator can't equal 0. But now it's not as simple as saying x can't equal 0. We have to figure out what x can't equal. If 3x minus 4 can't equal 0, I'm just going to add 4 to the other side. And then it says 3x can't equal 4. But that's not x by itself either. Now I've got to divide by 3. As long as x doesn't equal the fraction 4/3, that denominator will exist. So that would be the way to describe the domain. Or we could say from negative infinity to 4/3, and then from 4/3 to positive infinity. And I think we'll stop there. We'll focus on domain and range for these types of equations with the rest of our notes.